Over to you.
Okay, let's go to the next one.
The agenda slide is shown.
Okay. So why do we need synchronization in data centers? That's one of the first questions people ask. And what is the difference between a data center where synchronization is enabled and a data center where we have synchronization just as a best effort? Well, for the existing systems, synchronization doesn't do much, but we can design and build services that use clocks to replace communication with local calculation. And we have examples where distributed databases achieved significant throughput increase. We have example where we can manage the network traffic. We can improve the data consistency. And last but not least, we can improve significantly the ability for us to reason about the system and debug difficult cases. Today, I'm going to show you a few examples where clock synchronization and decreasing the clock uncertainty helps us a lot to improve the database throughput and the overall behavior of the system. Next slide. We know that the clocks are always being part of the database systems. We use logical clocks, we use physical clocks. When we moved to the physical clocks and we got NTP synchronization to the range of a few milliseconds, we were able to improve some of the metrics and characteristics of the system. But now we are in the area where the constant synchronization can give us synchronization in the range of hundreds of nanoseconds. And that is the time where we can see significant benefits. The reason is the clock synchronization always compete with our ability to communicate between the nodes. And when the communication is slower than the error bound, then we can start replacing communication with local calculation. Next slide, please. One of the first examples that we are going to take a look on is the external consistency. And when we talk about external consistency and clocks, we should, of course, start with the spanner implementation. But first, why do we need external consistency, and can we just go with serializability? Well, we've done that, and we know that it's much easier for the applications to consider a distributed system as a desktop database and to expect the behavior and observe the behavior. That's much easier to reason about. What is the external consistency? External consistency is a strict ordering of the transactions. So when a transaction ends, the transaction that starts after that clearly see the results, and more importantly, has a timestamp that is strictly higher than the timestamp of the transactions that finished before. Next slide. We know a couple of different ways to achieve external consistency. Spanner uses one of them, but it's not the only way to achieve external consistency using synchronized clocks. We can wait during the writes, as Spanner does. We can wait during the reads. As long as we have the right waiting period, we can guarantee that the timestamps are properly ordered. And here we're looking only two transactions, read after write, because two reads are not interesting and two writes are a different problem that are solved through different means. Read after write, we need to guarantee in the read after write that the read sees the results from the write. There is a third option that is also famous these days. The third option is used by CockroachDB, where we go with the reads and writes using just the timestamp, and later we abort and retry the transactions if we see conflict. I'd like to focus here that on the length of the wait or the size the amount of time that we need to wait. This time includes the clock uncertainty. That means if we decrease the clock uncertainty, we are naturally improving the database throughput. How much? Next slide, please. How much? We have data that shows us that in CockroachDB, by decreasing the clock uncertainty from 1 millisecond to 100 nanoseconds, we decrease the rate of retries from 99% of the transactions to 0.08%. This is a specific test. It's not true always, but we know that decreasing from 1 millisecond to 100 nanoseconds increase significantly the throughput of the database. Here on this slide, I'd like to tell you about a different case. Unfortunately, the slide is a PDF. Oh, okay, it's not, sorry, please, yeah, stop here.
Myself.
Yes, so let's stop here. So this is a different case where we have a leader and two replicas. The distance between the leader and the replicas depends on how we distribute them across the continent. But we have cases where the replica is far from the leader in the range of 100 nanoseconds. And 100 nanoseconds is easier for calculation. In the real case, it was a little bit less. But we have clients that are close to one replica and clients that are close to other replica. Regardless where the client is, if we want to get the latest of the data, we usually go to the leader. The leader is the place where we do the reads and writes to be able to get the consistent view of the database. However, if we have synchronized clocks, we might be able to do a little bit better. How? The client, no, just then, please don't go to the next slide. Yes, let's stay here. So how do we do this? When the client needs to read the data, the client chooses a read timestamp. And now the client can go to the local replica and wait until we guarantee that there are no writes that happen before this read timestamp. We can guarantee that by following or listening for the traffic that comes from the leader. The leader sends all the writes to the replicas, and the leader also sends heartbeats to extend the lease of the leadership. So if we set up properly the amount of data, the amount of traffic that we have between the leader and the replica, and we guarantee that, let's say, 25 milliseconds is the maximum distance between the two messages, then the client can wait until the read timestamp is strictly behind the write that comes from the leader. So instead of going to the leader and accumulating a latency of 200 milliseconds, we can go to the replica and wait about 100 milliseconds. In total, we're going to save 50% of the read operations, the latency of the read operations. And in case of a distributed database, that improves significantly the throughput of the whole system. Next slide, please. So this is a different case that as well includes the clock uncertainty in the total calculation. Here we have a service and a client and data that's owned by the service. The client reads the data and keeps the data in the cache. So in this case, we've had multiple clients in the range of thousands. And we also have data that doesn't mutate very often. We can keep the data in the client for hours and sometimes for days. If the data changes, and that might happen, the service must guarantee that all the clients receive invalidation of the cache invalidation. But that may not happen, or it may happen in the future that is very close to the read operations or write operations that the service executes. So we can optimize the system by introducing a strict expiration time for the data on the client side. And the expiration time includes not only the time that we include, but also needs to take into account the clock uncertainty. And if the clock uncertainty is the best effort, like NTP, we have to include, just to be sure, multiple seconds. If the clock uncertainty is the range of milliseconds, then we have a much tighter contract between the service and the client, and the service can confidently omit the cache invalidation, or the service can wait and delay a little bit the write operation. In some cases, that's allowed, to guarantee that all the clients got cache invalidated without any communication between the service and the client. Next slide. And this is the last of the 4 different cases that I'm including in this presentation. The leader election and the leader lease as an important metric in the availability of the system. Here we have a consensus protocol like Raft or Paxos, and we have a leader that executes all the operations, reads and writes. As long as the leader is alive, the leader must talk to all the replicas and extend the leader lease. The leader lease allows the leader to execute the operations that arrive to the leader. If the leader cannot extend the lease, the rest of the nodes are going to start a new election and choose a new leader. But even though the new election can be successful, the new leader cannot start executing the operations and cannot operate as a leader until the leader lease of the old leader expires. So what is the appropriate time of keeping this leader lease? This is a balancing between 2 requirements. From one side, we want to elect the leader as soon as possible. From another side, we don't want to elect the leader too often because this takes resources. So the leader lease has time span defined in the configuration plus the clock uncertainty. The clock uncertainty plays an important role when we choose when to start a new election and when the new leader can start executing the operations. By decreasing the clock uncertainty, we're improving the availability of the system. Next slide. How can we decrease the clock uncertainty? Well, today we have multiple different options. We have the NTP approach or protocol that was introduced many years ago. And today we can execute NTP in the data center. And if you look at NTP results, you can think about them as acceptable or good enough, because NTP can report a range of milliseconds. Unfortunately, NTP is the best effort. In case of higher load over the network or the machines, we can see we detected how cases where NTP claims certain level of clock uncertainty that's actually not accurate. So NTP is designed for different environment. We don't recommend NTP in the data center when we want to use clock uncertainty for use cases where the hardware is involved. For example, NTP is not appropriate, or milliseconds clock uncertainty is not appropriate when we talk about databases where we want to execute thousands of transactions per second. The OS level today manages the time latencies in the range of hundreds of microseconds. If we go to real-time operation system, that gets even faster, or the range is smaller. In a fast network, we can communicate, and usually data centers have very good network. We can communicate between the machines in the range of tens of microseconds. And if we go down to the I/O operations and disk, we are in the range of tens of microseconds. NTP or some other methods that don't rely on spreading the time in reliable fashion are far away from being applicable in these use cases. Fortunately, PTP today is sufficient enough because PTP can guarantee clock uncertainty that is smaller than ability to communicate between the nodes. And that's the place where we defined where we can use local calculation and where we must use communication. There are even better options than PTP, and if you can afford White Rabbit, you're going to be in the range of nanoseconds, single-digit nanoseconds. But today we're talking about PTP, and I think PTP is an answer of many of the problems that we have. Next slide, please.
Georgi, quick time check, 8.5 minutes to go.
Thank you. Here is an example from a database that's in production. I'm not sure that you can see the numbers, but the important part is on the left side. The first spike is when we started executing distributed transactions using PTP and commit wait. The protocol, the numbers are not as important. I think on the bottom of the graph, we have single milliseconds latency, and the graph is logarithmic. So on the first, between the first and second spike, we've been running the database transactions using PTP synchronization and commit wait protocol. So we confidently were running for hours without any spikes, and the behavior of the system was well under the maximum levels we put, the maximum latency we put for the transactions. After that, we have two tests that use slightly different approach that requires a lot of communication between the nodes. So here we're using a protocol that doesn't use time, but use communication. And here we don't see in this graph, but there is a significantly more communication between the nodes. We can see that communication can be replaced with local calculation. The very last run that we did was using commit wait with NTP. Not this one, the next one. Yeah, this one. So here with NTP, we quickly got to the point where the transactions were running for single-digit seconds instead of milliseconds. And even then, but we were not absolutely sure that we provide external consistency, because we were taking the NTP clock uncertainty and applying in the commit wait protocol. So this graph shows that it's highly unlikely NTP to be sufficient for executing for distributed database, especially in the case of the commit wait. Immediately when we get to a network, to heavy use of the network, NTP cannot provide the level of synchronization that we need to execute to execute clock to execute to provide external consistency and execute confidently and replace confidently local calculation with communication. Next slide, please. So here is the place where I want to describe what is actually the biggest challenge for us. You probably watched a few presentations where we discussed clock uncertainty in the case of spreading the time across the data center. Well, we know how to do this. We've seen this working at scale. We can have a grandmaster with clock uncertainty in about hundreds of nanoseconds, 100 nanoseconds. We have transparent and boundary clocks. Each of them introduce uncertainty of about 50 nanoseconds or less. And we have ordinary clock at the end of this tree, of PTP tree, where the clock uncertainty is another 50 nanoseconds, extended by another 50 nanoseconds. So in total, we have about hundreds of nanoseconds between the grandmaster and the ordinary clock. So we can expect two machines across data centers to be in the range of 100 nanoseconds of each other. And we expect the clock uncertainty range to be confidently delivered to these machines, but only to the physical clock on the NIC. We are facing a lot of challenges on the software side. The NIC has a clock that is accurate and precise, and we can manage this with high level of confidence. But that's not sufficient for us if we want to build a service or application that relies on the time. Because between the NIC and the application, we have multiple layers. We have PCI bus that, even though can timestamp the messages, today most of data centers don't have this equipment. We have the kernel, Linux and Windows kernel. None of these kernels are designed to be real-time kernels. So they're going to introduce level of latency that is hard to predict. We also have a library that is designed, the time API, the standard time API library is designed decades ago. And today, the library itself is not where the most uncertainty is introduced, but the library does not provide this clock uncertainty. The library gives you a number, and this number is not sufficient to reason about the time across data center. And the application itself, it's usually multi-threaded application that is in the hand of the scheduler of the kernel. So when and how you get the time, it's kind of challenging. We have very accurate and precise time at the NIC, and at the application level, we have significantly more clock uncertainty accumulated between the NIC and the application than between two data centers. So this is our challenge. How can we improve the software stack to be able to utilize the results that we have at the NIC level? Next slide, please.
2 minutes, exactly on time.
Call to action. TAP, Time Appliances Project, is the place where we have discussions. How can we solve or how we can improve the software side? If you're interested in this topic, if you want to discuss and help us to improve our ability on the software side, to get the precise time from the NIC to the application, please join us. Thank you.
Georgi, thank you so much. I think this problem, I'm judging by the faces of the people in the room and they're nodding, is very much true and close to their hearts. And let's see if there are any questions. We have the last 2 minutes. Is there anyone online or here in the room with questions? So Georgi, this is this is the third work stream, and you will be leading it, and we are very thankful for you and the team that we will gather around this work stream to do this very important work of improving the accuracy within the software stack to match at least that of two data centers.
Yes, please join us.
All right, so thank you very much for today. Come join us next time in the room.
Thank you, Awad.